So let me start. May I start?
Yeah.
Okay.
So today the speaker is Petr Grinevich, Grinevich, and he will speak. I actually don't remember the
Okay, let me explain. But I would like to. It will be something associated with totally positive Grassmannians, MM curves, and the reason I present in here because I have impression that when we wrote the first text, we didn't understand that we have to use not Weyl but Cartier divisors. And now I would like to ask your opinion. Okay. First of all, let's start from motivation. Consider Cartier-Constituashvili equation. X equals to 0. First of all, one reason why it's interesting, because it was paper by Krichever who pointed out that if we have generic Riemann surfaces, we can associate solutions of Cartan-Petr equation. So it was famous construction. You have a Riemann surface plus a marked point plus divisor, and we construct solutions of Cartan-Petr equation. It was important in both cases. But now I would like to stress, we use sign plus. There are two topics. We can consider complex solutions, or we consider real regular solutions. Regular solutions. If we work in the complex domain, it's not important which sign we have, plus or minus. We simply can replace I to II. But if we discuss analytic theory, we would like to select a real regular solution. The sign is important. This equation is called Kp2. Kp2, Cartan-Petr 2. If you have sign minus, it will be Cartan-Petr 1. Of course, in some books, this equation is used as a model of water waves. Of course, it's a delicate question. But if the depth is about 1 centimeter, you have to use Kp1. If depth is not too deep, what is not too deep, but much deeper than 1 centimeter, you have to use Kp2. First, the question was the following. Let me recall Krichever construction. Assume that you have a Riemann surface, algebraic Riemann surface, gamma, with marked point P0, local parameter 1 divided by zeta. I prefer to use zeta is a function defined in the neighborhood of P0 and locally defined. And it has first order pole. You have divisor. Gamma 1, gamma G. D. Therefore, points.
No, the divisor of what function? Or
Okay, let me tell. Collection of points.
just any divisor.
Yes, some collection of points. I start from formal, and then I will go to, okay. Also G points. G is genus. Now points equal to genus. Then it's possible to prove there exists a unique function, of course for generic data, psi gamma x, y, t, with the following properties. Is one, meromorphic outside P0. Therefore, the function outside the point P0 is meromorphic. Divisor of poles. Okay, these functions permit to have at most first-order poles. Or you have these poles, you have the corresponding linear bundle. And third property is at P0, it has insertion security psi Yes, Baker has a function. Such is Baker-Heiser function. But the question is the following. It's generic construction. It doesn't differ between KP1 and KP2. But as you would like to construct real regular solutions of KP1 and of KP2. I'd like to focus on KP2. If you would like to construct real regular solutions of KP2, you have to impose some extra constraints on the data. The constraints were found Dubrovin-Natanzon, there was paper. They prove they are necessary and sufficient. Also, Krichever derived it from periodic theory by the constraints are found first. There exists an anti-holomorphic involution tau. So, on the curve gamma, we have complex conjugation. Complex conjugation is defined. Complex conjugation means that we have some anti-holomorphic map such the square of this anti-holomorphic map is identical map. Second property, most interesting. It's M curve. Because consider the set of all fixed points. There are some curves, there are ovals. And the number of ovals can be equal or greater than G plus 1. M curve, G plus 1 real ovals. Yes, it admits some anti-holomorphic involution. It's mean, yes, it's mean real curve. In some sense, it's a real curve.
Excuse me, can you remind the definition of an anti-holomorphic map?
So the anti-holomorphic map, okay, if you introduce local coordinate and you consider conjugate, okay, you have local coordinates. Z. Okay, if f bar of z holomorphic, then
So just conjugation?
yes, a holomorphic map. Locally, of course, locally. But of course, in fact, it resembles that, of course, tau on the complex plane, the standard, some generalization. But okay, it's if you introduce local coordinate and consider conjugation, it will be holomorphic. Or you can write in the other way. Some Cauchy-Riemann equation, but anti-Cauchy-Riemann equations. And let me draw a couple of figures. Two examples. One example is the following. Suppose that we have a plane. Consider such a curve, you see. And the tau is a reflection with respect to the plane. Real ovals are the sections of the curve. Genus is 3, and we have 4 real ovals. You see. It's an example of an M curve. Because you have 3 handles and you have 4 fixed ovals. And let me show non-M curve. example. Example is the same. You see. Okay, you have genus 2 and you have one oval. You see. The both scars are real. Now, we denote the ovals by omega 0, omega g. I start enumeration for 0. Next requirement, that P0 belongs to omega 0. The essential singularity lies at one of these ovals. Lies on the ovals. And also, now zeta is zeta bar. And the last condition, that gamma. So we have G other ovals, and each divisor point belongs to this oval. So each divisor point has a personal oval. It means that you have dynamics. It could not leave his personal oval because you have reality constraints. But singularities arise when divisor point reaches P0. But P0 has its personal oval, and all other divisor points have personal ovals. Therefore, the solutions are regular. So it was construction. Okay. But another. If you, there are so-called multi-line solitons. By the way, they are rather interesting. I don't know. Maybe I'll show. Okay, I don't have projector, but nevertheless. Okay, example, some solutions of KP and some real water waves. Of course, it's a little delicate because paper by it's Baldwin, phys E. But nevertheless, you see that locally they are like one-dimensional walls, the solutions. But they may form rather complicated structure. Moreover, okay, I'll remark in a moment, and how to construct such solutions. You can use Darboux transformation or something like this. So you have the following data. First of all, you select K1, Kn, and numbers. Okay, let's do again. We start from complex case, and then we select real regular case. Complex solutions. You have some n complex numbers. You have matrix K smaller than n. You have matrix A. 1, 1, A. 1, n, A. K1, A, K, n.
Arbitrary data.
Sorry?
These are arbitrary data.
Yes, this moment. So we have a matrix. We have the following data. Collection of numbers, n numbers. And matrix with n columns and k rows.
So these are additional data compared
Different. It's, no, another approach. Forgot for a second about Krichever. Forgot for a second about Krichever. How to construct this? Krichever construction provides some quasi-periodic solutions. But you have also solitonic solutions. How to construct solitonic solutions? You have the following data. Matrix. Then you construct collection of functions. Fj A Jn, maybe not K kappa, I'm sorry, kappa 1, kappa n, Hn, plus kappa K cube T, sorry, okay. And with each line,
Is real or complex matrix?
for a moment complex, but then it will be real. For a moment complex, then it will be real. Okay. If you let me construct complex solution and then discuss how to select real solutions.
Problem. A small problem with the notation. You have the size of matrix K by n, and you use
Ой, L. L, 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 L. Okay, it's better, of course. You have this, construct collection of functions. Then you construct the matrix F1, Fn, F1 prime. Prime means dx. Differentiation is with respect to Fn prime, F1 and minus 1, Fn and minus 1. You construct Wronskian of these functions. We take tau is that. And now write u to dx square tau. So you do the following. You take this data. Then you construct Wronskian of these functions. You calculate the derivative. The second logarithmic derivative, or log tau by t. And then you, in statement, this function solves Katsuyt-Tversvili equation. But now, how to select real solutions? May I remove it? To select real solutions, you have to do the following. Well, there are two problems. We can select real solutions, or we can select real regular solutions. Sufficient condition was found by Melanyuk, he was student by Dubrovin, and later Kadam and Williams proved it's a very non-trivial statement that these conditions are also necessary. Okay, let me omit it, but nevertheless, to prove that these conditions are necessary, you require very serious non-trivial work, but these conditions first formulated by Melanyuk. First of all, assume that we need that all kappas are real. We require that all kappas are real. Of course, we can take kappas complex conjugate pairs. If you take, in this case, we will construct solutions which will be real but with poles. To construct real and regular solutions, you have to assume that all kappas are real. First condition. Of course, if they are real, it's natural to order them in the ascending order. Second statement, A shall be real, A are real, and third condition, that all maximal minus have the same sign. Okay, we may assume that they are positive because you can multiply one line to minus 1. So the maximal minus means that this, we consider I1, Ik. You take k numbers. Of course, we can assume that the numbers are ordered in ascending order. So we introduce minor delta I1, Ik. It means that we take all rows and we take columns I1, Ik. They are Plucker coordinates, in fact. And this condition is they have the same sign. For example, we may assume that they are non-negative. So we assume also a very simple remark. Assume that we apply we multiply A to some non-degenerate matrix. A goes to CA. C is real non-degenerate matrix. We see that this determinant will be multiplied to a constant tau. So the logarithmic derivative doesn't change. Therefore, the real data is not the matrix, is the space generated by the rows of A. So we have a point of Grassmannian. So we have a point in Grassmannian. So in fact we have not A, but we have a point in Grassmannian NK such that all Blücher coordinates have the same sign, or non-negative. So we have the following picture. What was our starting point, but I decided to start with introduction. Motivation is the following. Okay, we have two objects. We have totally non-negative Grassmannians. It was known, it's very classical, I think Krichever explained it, Mikhailov, that any soliton solutions can be obtained from finite gap if curve degenerates and goes to some degenerate curve. If we degenerate the spectral curve, gamma, we can obtain soliton solutions from finite gap ones. So from one point, on this side, we have totally non-negative Grassmannians. On this side, we have M curves and their rational degeneration. The question was, how you, so our problem was the following. Assume that we have this data. Kappas and a point in a totally non-negative Grassmannian. How to construct this solution from some by degenerating some M curves with Dubrovin-Natanzon divisors. You understand? So two objects was M curves and totally non-negative Grassmannians. How they are connected? It was our question. You understand the problem? Because also it was the idea by Sergei Novikov that if we construct real regular solutions from finite gap, the finite gap solutions shall be also real and regular. So we don't want to consider generic curves. We are in real algebraic geometry, not in complex one. So everything we are doing is some piece of some real algebraic geometry, not complex. No, real or complex, but nevertheless, real structure is critical for us. So it was our question. How to construct these solutions starting from this. Our answer was the following. Okay, let me remove it. As for if you have a totally non-negative Grassmannian, it was studied by Alexander Postnikov. And he considered cell decomposition for this totally non-negative Grassmannian. Of course, this totally non-negative Grassmannian topologically is trivial. It's topologically contractible to a point, but nevertheless, it has cell decomposition. It's maybe not very trivial, but there is. It was proved.
Okay.
I'm not ready to prove this moment, but nevertheless. So, Postnikov suggested a cell decomposition of totally non-negative Grassmannian. And our construction essentially uses the construction by Alexander Postnikov. So next step is the construction by Alexander Postnikov.
So am I correct or not? So as far as I understood, you said that this construction is necessary and sufficient conditions for solutions to be real.
Yeah, and regular.
And regular.
Yes.
only for the construction we showed us before, namely for solutions which are D2 of logarithmic.
Sorry.
This is true only for solutions you constructed before.
Ye-
The
Yes.
second derivative for the logarithm
Yes.
of tau
Yes.
function constructed as you
Yes. Yes.
as you
Yes.
already
Yes.
like,
Yes.
right? And second question, as far as I understood, you said that somebody proved that any such solution can be obtained as a degeneration from M curve.
No. It's our result that we demonstrated, we constructed M curve. Okay, in fact, we constructed degenerate M curve, but also it's possible to make it smooth.
Is it possible to go in the opposite direction? That is to say, you start with Krichever construction and you...
No, the problem is the following. In which surface we have to use in Krichever construction to construct this given?
So this is a particular case of that. So
No, it's limiting case. No, it's limiting case.
Your claim, right? This is your claim.
Yes, our result. Yes, no, our claim is we construct staying in the real regular class. So
Yeah, I thought that it was known before, or maybe.
no, the statement no. There was the following situation. Of course, it was clear how to construct multi-soliton solutions, starting from some curves. But from which curve we have to start to construct this given multi-soliton solution? Our question was. We have multi-soliton solution.
if you drop the assumption of reality,
Respecting reality at all moments.
if you drop it, was it known before?
I don't know. Maybe it's easy, but I don't. Nevertheless, okay. Maybe. No, of course, it was known that you can construct some multi-soliton solutions. But assume that you're given some multi-soliton solution. How construct this special multi-soliton solution? We have to show some curve. By degenerating this curve, we will construct multi-soliton solution. But we have to associate. We have a solution, and we have to associate a curve. It was our question. Moreover, in fact, we understood that maybe it is necessary to tell the following. What we are doing now, we can tell that we have these Postnikov cells. In fact, the Postnikov cells can be naturally treated as Jacobians of these rational curves. I think maybe it's also interesting that we have these Postnikov cells, Postnikov parameterization. But, of course, there is dynamics on this also. Maybe, I think today Talalay was mentioned also this. But our statement is that these positroid cells are in fact Jacobians of some MM curves. But it's... So let me explain how. So we have a positroid cell. How to show that this positroid cell, this cell decomposition, is Jacobian of some curve. Let me construct the curve. Okay, let me define it. So, the composition. First of all, we know that, assume that we have a matrix. If we have a matrix, first thing we to do, it's because we have freedom, and we transform it to reduce row echelon form. Because we have freedom, we have so for a point of Grassmannian, it's natural to use the canonical representation for a point of Grassmannian. Okay, so let's assume that we have a matrix, and let me draw an example. 1, 0, 0, 0, A, 1, 2, 0, 0, 0, 0, 1, 0, 0, A, 1, 4, and 1, 5, for example, A, 2, 4, A, 2, 5, zero, 0, 0, 0, 1, 0, A, 1, 7, A, 2, 7, A, 3, 7, 0, 0, 1, A, 2, 8, A, 2, 9, A, 2, 10, A, 1, 10, okay, 1, 9, and 1, 10, A, 2, 9, A, 2, 10, 9, A, 3, 10, A, 4, 9, A, 4, 10. So if you have a point of Grassmannian, we represent its natural uniquely represented by a matrix in the row echelon, reduced row echelon form. And then we count the numbers 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5.
How do you associate this Young diagram to?
Yeah, simply count the numbers of A
It's every line, it's every row.
in every row. I simply count the numbers of A in every row. You understand? A may be 0 non-zero at this moment. So this is a corresponding Young diagram in English notation. There are French notation and English notation. So it's Schubert. So this point of Grassmannian lies in the Schubert cell with this Young diagram. Okay. Then the statement of the Postnikov is the following. Now you have the Young diagram. How to, but the positroid cells, cell documentation Postnikov, is subdivision of Schubert cells. So they have Schubert cell. A Schubert cell is represented as a union of positroid cells. The positroid cells enumerate in the following. So, okay, as soon as we have some, okay, let me have this Young diagram. Then, to enumerate the positroid cells are enumerated by pairs. Young diagram, plus we have to mark some boxes in the Young diagram. So pair. So for example, you can, okay, let me make a possible marking. For example, the boxes are marked. It's not almost arbitrary, but there is only one constraint. The constraint is the following. Assume that we have an empty box. Such configuration is forbidden. We have empty box. We have a marked box above and a marked box on the left. Such configuration is forbidden. You see. If we have an empty box, all boxes above and all boxes on the left are free, or all the boxes on the left are free, you see.
Is it possible that all the blocks on the left are not free and all the blocks above?
Okay, this.
This is
Okay.
But they also have some free blocks.
So, no, okay. For example, it's okay. For example, this will be also okay, I think. So, no, this is not okay. Something like this is also okay. So if you have a box, you can reach the boundary through empty boxes going left to going above. So, but any other, it's the only constraint on the only constraint to the. So, if you select some marking, you select a positroid cell. And it's again CW decomposition of positroid cell. Now, next step is the following.
Does he define cell associated with this marking?
No, let me now define the parameterization. Next step is у Postnikov. Okay. Now the yes. First of all, now let's describe the parameterization of cells by Postnikov. The following. First of all, we have to construct a graph from the diagram. Transform this diagram into a graph. First thing, we write numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You understand the row. We enumerate the boundary. We enumerate the southeast boundary of the graph. You see. 1, 2, 3. Moreover, what are the numbers on the right? The numbers on the right are 1, 3, 6, and 8, you see. So, if you have column containing 1 and other zeros, the pivot column, the numbers are written on the right. If you have no pivot columns, 2, 4, the numbers are written at the bottom of the graph. Okay, let me draw a bigger picture. Two, 3, 4, 5, 6, 8, 9, 10. Sounds like this. Then we do the following. Okay, let's draw one, 2, 5, 6, 7, 8, 9, 10. We introduce boundary vertices. Then we do the following. We take any point and put, instead of star, we put a vertex of the graph. And go. So we take any marked box, put a vertex in the third, and go downstairs and go to the right. You see. And you obtain a graph. You see? You understand?
It's always possible to draw such.
No, what's the problem?
I just don't see why it is always possible to draw such.
No. You simply take any field box, put a vertex and draw a line.
Yeah, but possible. But
What does mean possible?
What is the problem?
okay, let me see.
But it's
It goes as not
disconnected, right?
It's not important, not so dramatic. It may be disconnected. It's not forbidden.
there is always something protruding from the bottom when you go down, so it doesn't matter.
Yes.
Yeah, here is what the question is. Is
Yes.
it possible that there is no mark, no point, so suppose take the point 9.
Okay, mates, it's not forbidden, but it will be so-called degenerate. Yes.
Take the point 9 and erase all the marked points above it. What will happen?
Okay, it will be in some sense. Okay, some points will be not connected, but it means it's possible, but it's some limiting case. In this case, we can remove the corresponding. We can reduce the size of the matrix. We can reduce the size of Grassmannian. So, but what's important? Why the rule is important? You see, if you have this. You see, why this Lie rule is important? Because if you have point here and we don't have here, you have non-planar graph. So the constraint is that graph is planar. I don't know why, but it seems that it's some experimental observations that planarity is deeply connected with positivity. So the graph is planar. So then okay. The next step is the following. We remove now the box, this. Borders. Let's see. So then we put orientation. Then we do the following. On each horizontal line, we put a non-negative weight. T12, T15, T17, T110. You understand the enumeration weights because it goes from 1 to
By 10, by 5, 1, 2, 1, 5. Where is 1, 4 then?
No one, because no vertex above the vertex.
So how do you choose the names of these weights?
the names are the following. In the first line, first is 1, in the second is 2, T67, T69, T610. You understand?
By 6?
Or maybe no.
It's above 6.
No, maybe, I'm sorry, they 3. They use T3. The first is the number of line. The first number is the number of line. This is, no, maybe 6, okay, maybe 6. 6, okay, why not 6? Because you see, it's starting from the no, yes, it's 6, 9, T6, 7.
From 3. Then you have T3.
3, yes, T3, 4, yes, 8.
Why the second is 4 then?
Yes, T3, 4. T3, 4.
Why the second is? It's where it goes down.
Yes.
1, 4, 1, 5, 1, 9, 1, 7, 1, 9, 1, 1, 7 probably. After T1, 5 there should be 1, 7.
Yes, 1, 7.
You have T1, 9.
No, 7.
That's 7. Okay,
T1, 7. Okay.
no, just don't see it.
Yes, okay, I'm sorry. And then the following is so, for example, we would like to calculate the element A37, parameterization. And also, it's possible to slightly simplify the graph. You see. Why? You have bivalent vertices. You have bivalent vertices. You can remove them, you see. Then A, K, L. First of all, the sign. So, for example, A37. What does it mean? You take the third line, starting from 8. And points, okay, A to 8, A to 6, 8. 8 sources. 2, 4, 5, 7, 9, 10. They're called sinks. You understand? You have two types of boundary points, source and sinks.
Sinks are the endpoints.
Yes.
Targets.
Targets. And sources are starting points. A, J, L is sources between also, let me introduce the following notations. I1 is 1, I2 is 2, I'm sorry, not 2, 3. I2 is 3, I3 is 6, I4 is 8. You understand? I1 is the number of the source in the first line. I2 is the number of sources in the second line. And equivalently, the numbers of pivot columns. I1, the first, the third, the sixth, and the 8. So it's between and L. So if you, for example, calculate A37, you have to calculate the number of sources between 9 and 7, you see. There are two sources, 3 and 6. This is, so if you calculate, okay, A37, you take the third line. No, I'm sorry, the third line take, the source 6. And No, here are no source. I'm sorry. A37 no sign. It's positive. No. Okay, for example, A19. How to calculate sign of A19? You take this, and see how many sources are between. 3, 6, 8. 3 sources. You understand the rule of sign. You simply, so, and
Between what and what? Between ij? What is ij?
ij, there is phone sign times sum of all passes from ej to L. So you calculate AJL.
What is it you wrote that the number of sources between ij and L?
Sources.
Yeah, the number of sources
Yes.
between ij and L. What is ij?
Yes, this is the definition of IJ.
Ij.
Yes. AJL. You consider all passes from IJ to L, but passes shall be go only left and only downstairs.
But there is only one path or zero path.
No, maybe 0, but maybe more than 1.
You can also turn.
If you have square, if you have squares. Assume. Okay, let me draw another simplest example. If you have something like this, now, as soon as you have such a graph, of course, we can go how to reach this point. We can go this way. 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 You can go this way. You see?
Does it have something to do with the number of Catalan paths, deep paths?
And also says, pass. Then we do the following. On each pass, we draw the product of T. You see? The weight of pass is the product of T on the pass. Vertical lines have weight 1. Horizontal have positive weights. So the weight of a pass is a product of all numbers written on this pass. We have to sum of the passes. Theorem by Postnikov. It provides a birational parameterization of the positroid cells. The procedure. Okay?
So, what sense parameterization? You mean
By T.
AIJs?
Yes. Okay, maybe let me show the simplest example. 2 by 1, 0, 0, 1. E to 4. Let's consider the simplest example. Okay, let's have a look. Let's first of all, we have a look. We have delta 1, 2 equal to 1. A to 4. Delta 3 is minus A. to 4 minus A. A to 3. You agree? And we have condition that all these numbers are, we have this inequality, that all the,
They are not just minors, they're also algebraic complements, aren't they?
sorry,
I thought that minors are just determinants of these submatrices. And you also take into consideration the signs. So when you plug in the signs, it's called algebraic complement.
yes, it sounds, okay. So, and so what's this, okay. Simplest example, you obtain the form. We have this diagram. One, two, three, four. T1, 3. T1, 4. Yes. What we obtain? A1, 3. T1, 3. Minus, sorry. Minus A minus T, 1, 3. Because you have between A3 and have one source too. So the sign is minus. Three A T to 3 T to 4 and equals minus T 4 minus
Only one source.
yes. And also we can check that automatically you obtain parameterization. You see that in fact we have 5 inequalities, but only 4 of them are independent. Sorry, yes, okay. Okay, maybe I have to, but no. The next step was the following. What we did. First of all, now the next step, first of all, what is possible to do? It's possible to remove all bivalent. No, first of all, what we do, assume that we have such a configuration. Then we replace configuration by, by the following one. You see, if you have 4 valent vertices, we apply such transformation and we obtain graph with only 3 valent vertices. 2 valent vertices.
But you could as well move the bottom arrow to the right instead of moving to the left. Couldn't you?
No, because, no, why not to move this way?
Yeah.
No, because we, on this graph, we can move down what the passes are permitted.
Yeah, but
If you make this procedure, make this. Originally we have this path. If we do this way,
You lose this path.
yes, we lose this path. And here we keep all the, you understand? It's the reason why. So we obtain three valent graph. So we obtain graph with only three valent vertices. If we have two valent vertices, we remove them. You understand? And we have three valent vertices of two types. Two sources. So, okay, first of all, we have such vertices. Two outgoing, one incoming. You understand? It's called white. And another option, we have one outgoing and two incoming, black. And I have forgotten that also we add. You see. So we have two types. We have bipartite graph with black and perfectly colored. We have oriented graph, and also we have vertices of two types. Two outgoing, one incoming, and two incoming, one outgoing. They are black. And then we did the following. Okay, let us, so we have a graph. And now we say, let us draw a rational curve dual to this graph. Consider a curve, a rational curve, dual to this graph. It means the following. First of all, we have this boundary. We replace it by CP1. This boundary. It will have gamma 0. Then we replace any point of the graph by CP1, any vertex. So any vertex, if white, we call it gamma k, CP1, and this also, this curve will be omega k. So,
You said you replace it with CP1, but you don't replace it with omega.
no, it's all CP1. CP1. First of all, we replace this boundary.
The boundaries are just all the sources and targets.
Yes, yes, CP1, one CP1. And other CP1s are associated with the vertices of the graph. By the way, why it's important to trivalent? Because if you have trivalent, you can always assume that the points are 0, 1, infinity. Therefore, we have no moduli. Such curves have no moduli space. If you have more than 3 points and one CP, okay, the moduli is only here, but if you have more than 3 points, of course, you have moduli. I don't know what's maybe some. And now we see that also do the following. We tell that we have CP1, but everything is real. So we do not draw the CP1. We only draw the real parts of the CP1. You agree? So assume that, okay, it's a simple case. We have this graph. Let me do with this graph what we do.
So real parts of CP1 are just circles.
Yes, circles. So you have 5 CP1 here, you see. And now we do the following. Okay, we also can do reflection. It's maybe.
Sorry. White when you have two outgoings and one inside.
Okay, I'm sorry. It's black. Yes, I'm sorry. So we have this. And now we do the following. We replace all every point by a circle. Simply. Now we tell that all the circles are real parts of CP1. And we glue the corresponding points. You see? Glue means that we have a function.
Corresponding in what sense?
No, you have a graph.
Yeah, you said corresponding points. What are corresponding?
For example, we had a graph. Okay, here. For example, 0, 1, infinity. Something like this. And here again, so we have graph. We have two copies of CP1. And we glue this point to this one on CP1. So we have graph, it prescribes how to glue points. The graph prescribes how to glue points.
Gluing procedure is in some algebraic sense, right?
It means the following. We have two spheres, and we simply assume that function is regular if the value function on this sphere equals to the value function on this sphere. Yes, this is algebraic procedure.
So is this some kind of intersection? Double
Yes, double points. We make them double points. So we have a collection of spheres with double points. It's our curve. Now, and our statement is, in fact, in this theory by Krichever, we can have a freedom. We can choose divisor not at the point 0, but at some other point. We can use different normalization point. Assume we have a generic normalization point. That we can calculate we can calculate the divisor. We have a point A, we have a point of Grassmannian, and we have a procedure how to calculate divisor starting from the point of Grassmannian. I explain how to construct the Riemann surface.
But first you need to construct.
Curve. I explained how.
First you have a matrix.
Yes.
Which is positive.
Yes.
You fall into some positroid cell.
Yes.
You draw the graph for
Yes.
the cell. Then you draw the curve for
Yes.
the cell.
And then we calculate divisor.
And how do you calculate divisor?
Or by some more or less algebraic procedure. Okay, maybe I don't want.
Okay.
No, it's not very difficult, but
It still takes some time. I think.
still takes time. But because I would like to concentrate on slightly different remaining part. What is my question? And we told the following: if you have generic normalization point or generic data, the divisor is located outside the double points. And if this divisor is located outside the double points, it satisfies the Dubrovin-Natanzon condition. And now we can desingularize the curve. We can transform the curve in the double points to small handles, and we can construct regular curve from. If you locally have intersection like equals to 0, we make x, y equals to epsilon. Of course, necessary to choose sign epsilon correctly to keep the M property, but it can be done. Okay.
M property?
The maximal number of ovals.
Maximum.
G plus 1 ovals. By the way, here is planar graph. So ovals are simply the faces of the graph. And first of all, what is the difference between black and white vertices? If a CP1 corresponds to a white vertex, we have one divisor point on it. Understand? If we have on black vertices, the function is constant. we assume that our Baker-Heser function is constant on CP1 corresponding to black vertices and fractionally rational on the copies corresponding to white vertices.
It's real. I mean, real.
Yes.
Because otherwise it would be a problem. It's complex analytic function. It cannot be a constant or something.
No, it's constant. It's not.
Because it's real, yeah.
No.
It's constant on the real part.
No, it's constant everywhere. No, real analytic function is constant function. On the whole, CP1 is constant function. You have constant function in the Riemann sphere, constant function.
Yeah. Oh, I see.
And if you have CP1 corresponding to white vertices, is fractionally linear.
I just don't understand how do you glue constant function with non-constant function.
No, because they have several components.
Yes.
On one component it's constant, on other component they're not constant.
Component in the sense
Algebraic geometry. Because it's
algebraic geometry. I thought it was one Romanian's purpose.
And the statement was that the divisor, but what happens? You may have the following figure. Okay, let me draw it. For example, this. And of course, you worked with Weyl divisors, you understand. Now, it's in some sense my question why I want to present here. But, okay, first of all, you can, how to interpret what we told. That we represented the positroid cell, okay, open set in positroid cell. No, we would like to interpret positroid cells as Jacobian, of real components of Jacobians of these MM curves. We call them MM curves. One M for Mumford, another M for M maximal. So MM means two. First of all, it's Mumford means that it's union of spheres with only, you see, minimal. And the second, M is maximal number of real ovals, two different M. So we call them MM curves. Now, but what happens? Let me say, for example, how Abel transform looks like on these curves. Because if you have a, for example, since we have this omega, we have corresponding bicycles. We would like to construct the corresponding Abel differential. How it looks like. It was written in papers by Artamkin, Turin. We looked to these papers. It was wrote. What does mean holomorphic divisors on the curves? Holomorphic. Holomorphic divisor means the following. Okay, path consider a cycle goes along some edges. You agree? Therefore, for example, path. Okay, for example, this point is 0, 1, infinity. Consider this component. The path comes in the point 1 and goes out at the point infinity. Then the holomorphic differential corresponding will be omega on this component will be minus dz and that minus 1. We use normalization 2 pi I. Okay. We use this normalization like in the Fay book. So holomorphic differential is this one. In fact, it has first order pole here. First order pole has the residue is plus 1, the residue is minus 1. This differential here has a residue plus 1.
So how does she divide it? The differential to divide?
No, I would like to define the basis of holomorphic differentials. Not me, okay. I followed.
So you have this curve.
Yes.
Curve.
What does it mean on this? What does it mean holomorphic divisors? Holomorphic divisors means that they are meromorphic. They may have poles at double points, first order poles, and the residue here is minus the residue here. So we glue 2 points. The sum of residues here and here.
These 2 points are actually 1 point.
Yes. No, but okay. Let me explain it. Assume that you have a very long handle. What does mean the differential is holomorphic? This cycle is this integral. Integral over this cycle is equal to the integral of the cycle. You agree? But if you look the cycles on the sphere, they have the opposite orientation. Therefore, the residue shall be opposite. But it means that you can move this through this.
Probably a double point.
Yes, through the double point. Because you would like to have the space of holomorphic differential of the same dimension as arithmetic genus. Okay? And to have, so you need, because you don't have naive holomorphic differential. You have spheres. On spheres, you don't have holomorphic differentials. So the holomorphic differentials means that they are meromorphic on spheres, and if 2 points glued, the sum of residues equals to 0. First order poles.
They are meromorphic, but their poles are
On these degenerate curves, they are holomorphic.
So in those spheres they are meromorphic,
But
their poles fall into the double point
Yes.
to each other.
yes,
Somehow.
and yes. No, but okay, it's natural. First, no, but it's to see it. Okay, consider simplest case elliptic curve. D lambda by square root of 4. Okay, this standard elliptic curve. You see it. You have its standard holomorphic differential on the elliptic curve. What happens if you have degeneration? Degeneration E2 goes to E3. In this limit, when E2 goes to E3, the limit of this differential is d lambda You agree? Okay. When 2 points, E2 and 3 cosine.
Well, I see what you mean.
Sorry.
I mean, when these 2 points merge, you get this differential.
Yes. They have. So you have this curve, E2, E3. When E2 goes to E3, you have double points. So the limit of this differential is this one. So it has first order poles with opposite residuals at 2 sheets. At 2 points we glue. Okay. Now, now we have, okay, return to this situation again. What we notice that we may have the following configuration. Of course, we know that each oval its face contains only one divisor point, Dubrovin-Natanzon condition. But what may happen? Say go to this point and then go this way. Consider the dynamics, how the zeros of the function, how it depend on x, y, t. We look for dynamics. Or another problem, we would like to have parameterization of the full positroid cell. So we have to consider not only, we call it smooth differential. Smooth means that differential do not intersect the locus. But we have also to consider differentials intersecting the locus. You agree? Intersecting the locus. So it may happen so these two differentials go from the opposite directions. And then they simply pass each other. But what's important? We can simply write Abel transform near this point. It will be something like A of D okay, plus. You see. Therefore, if we naively treated, we could not move this. If we go simultaneously to these points, to have the Abel transform continuous, we have to keep the ratio. You agree? Okay, we use Weyl differentials. Therefore, if you would like to describe this situation, you shall assume not only that both differential points goes to the double point, but to keep the ratio, to make Abel transform. My question was, does it mean that we pass to Cartier differentials? But okay, so we do the following here. But what we did, we simply told the following: we have coordinates, near this configuration, two divisor points pass through double points. So we simply do the following: we introduce Z1, Z2, but they are always real. Now we make standard resolution singularities. We make R2 times RP1 on the points. I think it's standard blowup. So if you use Weyl differentials, we have to apply standard blowup. After applying the standard blowup, the dynamics of divisors became regular. So if you would like to use Weyl divisors to parameterize the Jacobian, we have to do blowup if two divisor points. Another configuration is possible. No. I think consider the differentials on this has. First of all, in fact, the point Z1, Z2 in the, you see that, only in the two quarter planes located. And then we tell that these points, we introduce new coordinates now, but how to treat this procedure? This map. I think it's standard blowup or not.
Yeah, I just don't understand why you need blowup.
No, because I would like to have Abel transform regular. I would like to have regular Abel transform. Or I would like to have regular dynamics. No, because, okay, I would like to, okay, we have divisors and we would like to calculate Abel transform, we agree. But we have this singularity. Assume, okay, Z1, Z2, Z1, Z2, for example. 1, Z2. If both Z1 and Z2 goes to 0, you have singularity, you agree. But if you consider this function the function here, it's regular.
As long as this ratio is away from 0, right?
Yeah, yes. Yes. No, if the ratio goes to 0 to infinity, it's boundary. Such situation may if the ratio goes to infinity, Abel transform goes to infinity, but it may happen only at infinite time. It could not happen in finite times. But if both goes to infinity and Abel transform is regular in time. So you have a regular, it's linear function of x y t. Of x y t. Abel transform is linear function of x y t.
What do you call Abel transform? Because remember, Abel transform was concerned with integrating
Yes. Now I of d is matrix of integrals.
Yeah. integrals have to do with this ratio, so that's what I understand.
No, but assume that we calculate these integrals. We would like to calculate. Okay, let's calculate only singularity of these integrals. So let's consider only one singularity. H omega has divide, okay? Z2. Oh, I'm sorry. Z2 by Z. So we have this omega, her omega is dz by z. Her minus dz by z. So we have to calculate integral over dz by z up to the point z2. You agree? Plus integral of z1 minus dz by z. Integrate her. It's stable transform. You calculate the.
I thought that the integrals in Weber transform were taken over the basis of cycles.
No, up to the point. Up to the point. I will transform, we take integral up to the point.
Yes.
And we have this integral, of course, is this one. I omit in the regular terms. It's linear. We know that the Abel transform linearly depend on x, y, t. So it's regular. But it may be regular if the ratio has a well-defined limit. You see? So to make this function regular, so the correct definition of divisor, okay, let me repeat again, we worked with Weyl divisor. The question was, what does it mean divisor? We could not simply go that both points are in the double point. One is impossible because it goes to infinity, it never happens at finite times. But what does it mean divisor? The both goes to the double point. It may happen. But it's incorrect to say, because we have this integral. It's not enough to say that both are located, agree, at 0. This function is not defined if z1 equals to z2 is equal to 0. It became a good function if we introduce this blowup. Sorry.
You mean that on this, how do you extend this A of D onto this RP1?
Yes.
How do you extend it?
No.
Do you mean that this logarithm of Z1 over Z2 over Z1
It's fine.
defined
Yes.
RP1?
Yes. Yes. If
Z1 goes to 0 and Z2 goes to...
and this limit is well defined, this log is well defined.
Yeah, but if Z1 goes to 0 and Z2 does not go...
No, it never happens in finite times. It's on the boundary of the cell, not inside the cell.
in the cell.
But this happens, the both goes to 0, might happen in the middle of the cell.
Yeah, I see.
So if you would like, so divisors, if you would like to use divisors to parameterize the cell, you have to do this resolution singularity. Another way situation may be the phone. For example, let me draw. I'm sorry, I plan to use picture, but nothing bad. You have this configuration. And simultaneously, 3 divisor points go simultaneously to the double point. You see? 3 crosses simultaneously. It's also possible. So we have 3. But okay, we have Z2, Z3 goes to R3 times R2. Okay. Yes, I'm sorry. We,
I know, just
so again, and our statement is the following: assume that we have totally positive cell, means that we have Young diagram. I'm sorry, but I don't know. And all boxes are filled. All boxes are filled. Assume that we have not generic positroid cell, but positroid cell such that all boxes are filled.
Maximal size.
Yes. No, but of course, the most maximal will be if you have. Okay. Yes. Yes, highest. But then only these two types of blowups are sufficient. No more complicated situations could not take place. Our theorem is. But I'm sorry, maybe I was a little. No, but I tried to explain everything.
It was very nice.
So it's such a statement that only these two blowups are sufficient. But it's some geometrical restriction because we have Dubrovin-Natanzon constraint. Roughly speaking, we can see that we could, because, so, but my question was, does it mean that we go to Cartier divisors? My question was.
Actually, your divisor, your original divisor was Cartier because
Yes.
because these points were not located in the single locus,
Yes.
and by that reason it's Cartier divisor.
So it's nature.
And moreover, if you are talking about the parameterization of Jacobians,
Yes.
and Jacobians parameterizes Cartier divisor.
So yeah, so it was.
So you make a deformation of Cartier divisors. And I would suppose that when your divisor collapses, maybe you intersect some compactification of this Jacobian. Maybe you get
No, it's a normal internal point of Jacobian here. It's no normal internal points of Jacobian, not compactification. It's normal internal. Why it's interesting? Okay, so maybe, but nevertheless, okay, we can reformulate in the following. We have special Cartier divisors with Dubrovin-Natanzon condition, and we can say that they obtained from Weyl divisors, but they blow ups. Okay, maybe it can be reformulated this way. Connection between Weyl Cartier divisors.
I don't understand why do you need Weyl divisors here. So you can just play with Cartier divisors.
No, but okay, these Weyl divisors are points. Cartier.
Well, yes, but your original divisor was Cartier. You are moving along the Jacobian.
Yes.
The Jacobian parameterizes Cartier.
No, first of all, yes, but to obtain.
You can take the image of Cartier.
Yes, I
to
understand.
the Weyl divisor.
Yes.
There is a map, natural map from Cartier to Weyl. And in this situation, your Cartier divisors are positive.
Yes.
And they're effective.
Yes.
Effective Cartier divisors are embedded into effective Weyl divisors. And when you are moving them,
No, but
you can
no, but I'm sorry, I'm missing because we have many different Cartier divisors. But what does it mean Weyl divisor on such curve? Yes, first of all, yes, the reason was following. How we calculate explicitly the points? If we calculate the points explicitly, in some sense we use Weyl, you understand? Because our construction originally uses Weyl, because we calculate the position, the points.
one divisor is just the image of the Cartier divisors under the natural map.
But I'm sorry. So it means that you have, okay. But you mean that here many different Cartier divisors are mapped to the same Weyl divisor or not?
This is possible.
Yes. So we have this. So because we have, okay, we can tell that we have this Weyl divisor. But the preimage is two-dimensional space. So in some sense, we can compare Weyl and Cartier divisor for this special.
There is a big kernel in this situation.
Yes.
The big kernel of Cartier devices is go to 0.
Yes.
By that reason, but I think it's more correct
Yes, I agree.
And look at their image.
Yes.
In the Weyl.
Yeah, so yes, in some sense, so what we did, it was transition from Weyl to Cartier for this special. Okay. Okay.
I think it will be more correct because this map has a big kernel.
Yes, I agree.
And I think,
And exactly this kernel is this one. Yes, in this situation. No, of course, I understand that. No, my statement is that for generic situations, the kernel may be very big and difficult to study. You agree? In this case, we can explicitly study the kernel because we have.
the kernel consists of divisors, of Cartier divisors which are not effective.
But okay. This case, okay, we have this configuration.
But your divisor is effective or not? I mean, your original divisor was effective, right? Because
Yes,
it's
3 points. 3 points.
sum of 3 points without.
With coefficients 1.
Yeah, then it's effective. Effective, this means that the coefficients of
Yes,
points are
yes, positive. We have effective divisor. And then we tell that, okay, this is one Weyl divisor, but many Cartier divisors. Is it correct? This is the kernel here.
I think the kernel was not necessary here because you move inside effective Cartier divisor.
Yes.
You form effective Cartier divisor, and they remain. And if your singular point is an internal point of the Jacobian,
Okay, sorry,
it's again.
Yes.
You either give a definition of Weyl and Cartier divisors, or we stop this discussion altogether, because I feel totally lost.
I'm sorry, but yes, but in some sense we studied the kernel of the map for this special with the special reality constraints.
So what is a Cartier divisor?
We can discuss it separately.
Okay, maybe later. Maybe let's. Because also I'm not a little new for it.
What is Cartier divisor?
Cartier divisor is a section of some special shift. It's a constant shift factorized by, well, it means that it's locally is given by covering and the function on it, the theorem of a function. And on the section, the ratio of this function must be inverted. This is the local description of Cartier divisor. So Cartier divisor locally is given by one equation, by one rational function. And then you can look at its support. It can be positive or negative. So
Yes.
that means that this can have full or zero. And then you can consider the image of this Cartier divisor into a Weyl divisor.
Weyl divisor is just some sort of point.
Oh, yes.
Some
No, but the reason was for me was more is simpler to work with points. Yes.
What conditions?
some coefficients.
Some coefficients.
Yes. For me, it was easier to think, of course, when we did this transform, we calculated the points in some sense.
But
Yes.
here is not correct because you try to parameterize.
Yes, so we have,
Jacobian.
yes,
Jacobian is probably space of Cartier divisor,
yes.
not Weyl divisor.
Yeah, so yes, so in some sense we may say that what we are doing, we connect in Weyl and Cartier description for this.
I'd like to say that you just described the movement of Cartier divisors.
Yes.
Weyl divisors are just absolutely not necessary here. You can meet the Weyl divisor description.
Yes, I agree, but yeah,
Only to describe this
Yes.
Local
Yes.
points.
Yeah.
I'd like to say that you just use the image of Cartier divisors under this
Yes.
cycle map.
okay,
Natural cycle map. But if Cartier divisor is effective,
yes,
then the image is injective.
yes.
And by that reason,
Injective or not? Sorry, something, no, I don't.
for effective Cartier divisor, it is injective.
But sorry, okay, I would like to discuss the situation. Because in this case we have to do, because we tell that we have this configuration. Okay, Weyl divisor. In some sense, is it correct or not?
If it is effective,
What does mean effective?
the coefficients are positive, not all positive.
But I'm sorry, what does it mean? We put point here, and point here. Is it possible or not? Yes. So, and for this divisor, we have many pre-images. We have.
We don't need to consider pre-images in complete divisor.
No.
You move again. You at the beginning.
Yes.
Before any movement, you have just complete divisor or white divisor.
Yes.
It is the same. And if you are looking for effective divisor, then this cycle matrix injected. And when you deform your complete divisor, your
Yeah.
effective complete divisor,
Yes.
remains effective complete divisor. You get effective Weyl divisor.
Yes.
The kernel is big, but it consists of not effective divisor.
No, but sorry. But okay, but I would like to understand the specific situation. Yes. Maybe this example.
We can discuss.
Okay, let's discuss. I would like to understand because I'm sorry because in some sense we first approaches was naive. We simply told that okay to make yes we have to the resolution singularities to make blowups to solve because. But now we are, okay, maybe it's, but it's exactly the reason I wanted to present it here. Thank you.
Complete divisor also, there is also this rational, local rational function.
Yes,
Shows you where the points are.
Yes. Complete divisor is the same as a locally free shift of one.
Yes.
But Weyl divisor is just purely geometric notion.
Yes.
And what's most important, if we are playing with Jacobians and we are playing with complete divisor.
Yes.
This
Yes.
Weyl divisor.
Yes.
And
This construction doesn't look like complete divisor.
it is.
Yes.
Because
Actually,
the positroids parameterize Jacobians.
Yes.
But when the points are
yeah, but this
when-
construction.
Moreover, I think it's maybe
This способно это blow up, но это развитие все-таки там где другого размера.
Здесь изначально точки были локусу.
да.
А как раз они, наверное, особенно локусу, то дивизор в этом случае в смысле то же самое, что дивизор карте. Просто образ дивизора карте
Потому что конструкция, которая написана была, что это ну, там, N, там, F2, F1, это не похоже на конструкцию. Это как
Я
геометрическая
вообще не
сторона.
понимаю, зачем тут что-то разбивать, потому что тут конструкция, которая вот ее делает гладкой, это скорее исключение в семействе. Вот эта вот модификация на эпсилон, это не раздутие, это включение.
Нет, мне кажется, раздуть естественно, потому что когда делаем...
Раздутие здесь как раз наоборот неестественно, потому что, по-моему, здесь нет никакого раздутия. Вы
Как?
включаете эту кривую,
Не
слой как слой выраженного семейства. И в этом семействе...
Мы кривую не трогаем, мы дивизор. Мы на дивизорах раздуваем, а не на кривой.
Не-не-не.
На пространстве дивизоров.
Кривую
Э,
перед этим, когда вы говорите.
Нет, мы делаем раздутие на дивизорах, а не на кривой. Кривую не трогаем, мы делаем раздутие на дивизорах. Вот это вот. Как бы. На пространстве дивизоров раздутие.
Ну, до этого вы говорите, что можно вот это вот...
Это другая история.
Это
Да.
другая
Другая история.
история. Вы рождаете вот
Да.
кривую особую
Да.
из неособой.
Нет, а сейчас мы просто делаем раздутие именно на дивизорах, а не на кривой. Это в том-то и дело, что мы на кривой.
Зачем там, я просто не знаю, зачем вообще там делать раздутие?
Нет, ну, понимаете, мы исходно получали, мы умеем вычислять дивизоры Вейля, как бы, ну, исходно. Можно, конечно, перейти.
Сказал, что это все-таки Weyl. Это, с моей точки зрения, мне кажется, более правильно говорить о дивизоре как дивизор карте.
Может быть,
Носитель. Это просто носитель дивизора карте.
можно и так говорить.
Потому что вы двигаетесь вдоль Якобиана.
Да,
И вы остаетесь внутри него.
да,
Значит, даже когда вы в этих носителей у вас
Да.
сталкиваются особую точку, это все еще
да.
образ хорошего дивизора карте.
Да, вот это и был мой вопрос. Это как раз мы и начали понимать. Просто, знаете, тут просто проблема такая. Если быть честно, мы раньше с карте никогда не работали.
Ну, я вам могу просто...
Я с удовольствием, нет.
Ну, давайте я просто...
Да, да,
Как оно...
Да.
Потому что вдоль оно точно пишется, это отображение цикла.
да. В общем, это нет. Это очень, то есть это действительно, то есть, значит, я просто хотел как раз и спросить, что...
Ну, мне кажется, что более правильное. Просто, ну, я просто могу нам
Да,
нашу статью покажу вам, и мы немножко об этом.
да,
Там просто есть. А просто это очень конкретно.
да.
Этот управление циклов. Вот.
Саша, давайте приведем такой
Да.
Да, спасибо. Да, спасибо.
Спасибо, это было интересно, но, конечно, технические подробности.
Ой, и-
Я так и не понял, это вот а также надо было параметризацию. Почему это именно я не понял. То есть позитроидные клетки параметризуются этими это я понимаю.
Нет, утверждение такое.